Hello and welcome back. Today I want to talk about a little bit about antenna splitters or power dividers, passive, resistive and active. First a little bit in general and later a little bit about the GPS or GNSS splitters, which needs to be active, and I will also explain why. Well, I have many GPS DOs and I didn't want to put a lot of antennas on the roof, so I use one antenna and I am splitting those to my receivers. And not only do I have three here, I also have an active extra connection for if I want to quickly test another GPS DO that I quickly want to test, or I have here a generator up here that can also be connected to GPS DO and also base his frequency on that. And I have two older ones also there. So up here I have also three. You can see on the left that is my active splitter right here. I have a little NTP server, but I also have some old-fashioned GPS DOs. They do GPS only, no other networks. But this is the Repco from the UK. I have here a Dayton or Symmetricom that is from the US, and I have another one from Europe, actually Italy. It is Eurolabs. They also do a lot in aviations. Pretty cool to test those, but of course I also split because otherwise I already needed 6 to 8 antennas. Going back to my main GPSs, this is my permanent one. I program it now for GPS and Galileo. This is the other one. These two are only switched on when I'm in the lab, so I just switch them on. So they just try to sync still. This is with GLONASS. This is with GPS only. Usually those type of GPS DOs just come with this active antennas, because the signal of GPS is very low. It's like minus 135 dB, I think. So it's very low. It's really inside the noise, and somehow they are able to get it out still to receive the signal. But these antennas are active, so it has a little amplifier inside. It's actually an LNA, low noise amplifier, probably with filtering also, so they only amplify the signal that they need around 1575 megahertz. It's quite a bit, and they amplify it also just to, because this is like 5 meters, make sure that the losses of the cable are also compensated for. I think some of them even amplify like 30 or 35 dB. Actually, it's quite a bit. But what I did find out, and that's why I have the splitters, if you put this on the roof, because first I had 3 or something on the roof, but if you put them too close together, somehow they interfere, and then they both have a bad signal. And if you put them further away, it gets better. Well, I needed 6, so that didn't work for me, because I have only one little chimney where I can put it on the top. So I went back to 1 and then have a splitter. So I started to look on the internet about active GPS or GNSS splitters, because, well, you saw already I don't only have GPS, so I have also GLONASS, Galileo, so I wanted to look for GNSS active splitters, and it's easy. You find a few. I found them. I will show you. So you easily pay around 200, 300 or 400 depending on the brand. So I wanted to look a little bit for alternatives. So one of the solutions would be a simple power splitter, power divider. It looks like this. I can zoom in a little bit. I think these are called resistive tees, and it's very simple. These are made for 50 ohms, and I just put here resistors in series in kind of a Y or a T, depending how you look at it. It has one input, and then it splits it into 2, and you have your split, and it is done with only resistors. The point, of course, is you cannot just put them in parallel, because it's 50 ohms, and if you put 2 receivers on the end, you will get 25 in the end. Well, with these resistors in series, you, instead of 25, you have again a little bit more. I think it's 16 ohm, so you have always 16 here, and then you have 16 here, 16 here. So between all the connections you have like 32 ohms. And then I don't know how they come with the parallel 25 and then somehow it becomes 50 again, but it is probably a trick they do. If you want 4, you just add 2 more here and then you have 4. These are the cheapest. You really pay a few dollars for this because it is only resistors, and the connectors are probably the most expensive part. And because it is resistive, it works already starting from DC all the way up to a few gigahertz. And then you have these are not purely resistive, they also have tracks here with inductions and they have coils, and this is much more for a specific frequency range. This one is for 2 ports, but you also have them more professional here. Then they become already a lot more expensive. I think new, these are around 150 euros from this brand, but that is also, these are also made for transmitting and they can do 10 watts. And of course for receivers you don't need them for that high power. But this is a limited frequency range. You can see here this is from 1000 to 1800 megahertz. So this would be in the range of the GPS. And when we look inside, this already looks a lot more fancy. This is much more made for RF signals, as you can see. And yeah, this is a higher quality. I show a picture of the real brand. I bought this secondhand in the AliExpress. I think, I don't remember exactly, I think it was somewhere between 20 and 30 dollars. I found out the real brand, so I show a picture. Why would you do so complicated if you can also do it like this? Well, the answer is very simple. This one is great because it has a very big range. Now it can go from DC to in the gigahertz, but doing it like this, you lose like 6 dB. So if you want to go to 4 channels, you already have 6, and 6 you lose 12 dB. And with these, you only lose about 3 dB, but also the isolation between the channel is a lot bigger, because here the isolation between the channels, yeah, is only this 16 ohms. So when you short circuit this one, you will notice that a lot on this channel, while if you use these RF tricks, the isolation is, I think, like even 30 dB or more. This is really great stuff. So that made it already very clear to me. The resistivity is not the one I want to use, because the satellite signal is so weak. They even need to amplify the antenna to get rid of the losses in this 5-meter cable. So that means if I'm going, and cable loss is usually really below the 10 dBs, no, 1, 2 dB, maybe a connector, maybe half a dB. So if I'm 1 to 4 channel and I'm already losing that 12 dB, that would be too much. Then I have no signal left after I've split it. So then I will come probably into something like this special frequency range with all this magic RF stuff. And well, then with the 4 channel you lose about 6 dB. So the only thing you need to do then is compensate for this 6 dB. So let's say I'm going to use this and I want to amplify that also. Then, well, I have of course first my splitter with all this RF magic. But then I need to compensate. So this is my magic splitter. But we lose here 6 dB. So we need to compensate. So then what we put an LNA, and a low noise amplifier that needs at least to compensate for the 6 dB here. But when we start amplifying, we also start to amplify noise, because the LNA, depending of course on the type, maybe amplifies from close to DC all the way up to a few gigahertz, and we only need the amplification between, well, I think 15, 70 until about 16 and a bit, and the rest we don't need. So what we could do is put in a filter and bandpass filter, so we only pass to the amplifier a frequency range between this. And then also after we amplify, we maybe want to put an extra bandpass filter here, but the bandpass filter also will lose some signal, so we maybe want 20 dB. And so the loss we have here, we can compensate, we amplify a lot, and then the loss here we also amplify. What if we want to put it all in a little box? Well, if we have the GPS antenna on this side here, we need to power that, because there is an LNA also in the antenna, so usually that is fed by the GPS receiver, GPS DO. So what we can do, we can power it from the GPS, and that's usually done 3.5 volt or 5 volts. And so what we can do, we can put here a DC block, we get the voltage from here, and we can just put it into the amplifier, and also we put a DC to the antenna like this. So then we already have a nice system, and we don't need to buy this $400 GNSS amplifier. Well, what I also read about is that some GPS DO have detection if there is an antenna connected or not. So we also do the DC blocks here. Then what you can do, you can put a little resistor here to ground, just to make the GPS 1, 2, 3, 4, just to make it think an antenna is connected, and it only needs to be a few milliamps just to fool it. So the GPS DO DC voltage goes like this through the antenna, and then the GPS signal back from the antenna goes through the filter, through the amp, through another filter, and all distributed to the GPSs. But we can also buy it complete, and we don't need to spend 400 euros. So I found this one. This one was also on AliExpress, and it also said GPS DO splitter. I bought one. This one was really like $24, I think. But if we have a closer look, it is just a normal distribution amplifier. And the range is from 100 kilohertz all the way up to 300 megahertz. So this could be used as a distribution amplifier, but only for the 10 megahertz side of the GPS DO, not the antenna signal, because that one was around 1500 megahertz. So this is sold as a GPS DO splitter, but in the end it is just a distribution amplifier, but you can use it for any receivers, and it seems to work great. Then I found this company, and this is a radio ham who designs this stuff. It is SV1AFN, if I read correct. And he's doing this for a few years. I bought one a few years ago, and it still works. And now I bought a second one. And this is the version 1 with the black PCB. And I like to have a look at it under the microscope to see how they did that. Because I made a quick theoretical drawing, and how is this done in practice. And I now also have the V2. I don't screw it off the wall, but I will also have a look inside, and we compare those with the microscope, because the V2 has been improved for a wider frequency range. It seems a ham radio call, and he knows his stuff in RF. So he has a GPS DO 10 MHz isolator and distribution amplifier. He has some LNAs, but my main thing here was the amplifier. Right here, the GPS antenna splitter, and it says here already GLONASS, Baidu, Galileo, and it is only around 99 euros, and it's maybe $120. I'm not sure if he exports to the US. And it's pretty cool, because it already has the amplifier inside, it does have the splitter inside, and now even it says here it is a new version. And I have both, so I like to see what is the difference. It is here already from 1160 all the way up to 1610, and I think for, I don't know, one of the standards needed to be a little bit above this 1600 megahertz, because usually you are all around this 1575 megahertz in the L1 band. But it is kind of a broadband signal, because the signal is so low. I think they do kind of a trick that it is like a few megahertz wide even, and that's why they can get more signal out of the noise somehow. I don't know exactly how that is done. They do have an explanation how that is done, by the way. If we say here, they talk here about it is 135 dBm, which is really low, 0.035 microvolts. I think if you have a real good receiver, just a broadband receiver, that it is 0.1 or something, so 0.05 is already very good. But they seem to do a trick here, the signal very broadband, and that's why they still get a positive signal noise ratio. They explain also what they do with the filtering and with the LNA that is inside, and why they choose a certain amplification of the LNA just to compensate for exactly the signal that they need. I have both, so let's have a look in the microscope. And here we have the version 1. You can see, because it's a little bit slightly damaged there, because I hang them on my wall. And this one is a lot newer, and I don't see a real difference when we look at them side by side. Even the front plates, they didn't even change. I still see the same serial number or design number here on the front, and here we see the output 2, 3 and 4. Here is the DC block, but there is that load resistor to fool the receiver that it is connected to an antenna. And here we have the main side, so the antenna goes here, and here goes the first or main GPSDO receiver that outputs also the DC to the antenna, so the DC goes directly to this port, and it doesn't enter the other side of the other antennas 2, 3 and 4. So 1 in, and we have 4 outputs. Well, we see here the V1 and the V2 are still very similar. And here we have both models on the inside. Before we dive into the differences, I first want to have a look at the version 1, and that is here the black one, and here this is the version 2, or at least this was my version 2. I don't see what revision it is. So I would think, for me this is version 1 and this is version 2, but I don't mention any versions on the website. So they made some changes to this board, why it has a broader frequency range. So diving to the version 1. So here we have it, and when we look, this is probably the input. We see here an FL1, this could be a filter. We have, I think here is a connection from this side to here for the DC. Then we have here a little coil, this seems to be an amplifier. Here we have another FL2, so that's the other filter, and here we have the power splitter, power divider. Of course it doesn't need to be that big as we saw in the metal box that I bought, because we are not transmitting here, so the signals are very low power. It's just a receive signal. So it seems input, we have here a diode, just to make sure for reverse polarity, I think. Through a coil, through a filter, through an amplifier, to the splitter, and then back out with the DC block, and some load resistors here to fool all the receivers that is actually an antenna connected. Let's have a closer look at the components, and I think we can start here with the filter, if we can find out what it is. Well, here we have it a lot closer by, and this says FL1 and here it says FL2, and well, this is the filter, and luckily they didn't put all the component numbers, so we will have to search for this. But this is the QZ series U5, and oh, here we have the op amp. It only says A, so that will also be a challenge, but I did find something. I'm not sure it is exactly that, but I think we do get a great idea. So I just started searching for the package that it is in. Here we have the pictures. It looks kind of similar. And I looked at GNSS and GPS, and I looked for a bandpass filter specifically made for this. And here, instead of the ZQ, and that is probably just further in the range or an older type, it says here ZC. But we can see here, so I have a good guess that it is from sort of one of these suppliers. You can find here one filter exactly made for GPS for L-band, L1 band, Galileo. So I opened one of these specifications, and here we can see, well, it looks very similar, only it doesn't say QZ, it said CZ. But anyway, it looks kind of a filter that we have. So, okay, they did some nice filtering. We can see what frequencies, what is the loss outside of that band. And, well, a lot of technical, but they did proper filtering. And then we have this LNA op amp with only an A on it. Well, I did find something. And apparently it is the NJG1130KA1, and it is, well, here we see a GNSS, a low noise amplifier. I forgot how I found this. Maybe I looked for the same brand as the filters were made, and then at some point I found it. I apparently used ChatGPT to find it. I did make a screenshot of it. I was looking for a GNSS LNA chip with the letter A on it, and it came back with, yeah, you probably need this chip. So that's how I found it. And later in the document, I found it was indeed an A that they use on the package. And well, the main amplification is here indeed in this 1575 megahertz. It is specially made, so yeah, the peak is really where it should be, and outside that band it is a lower frequency, lower amplification. A lot of specifications, but what I'm actually looking for is why do they need so much filtering? And here we have gain versus frequency, and we see that it is not a nice mountain and that nice mountain in the main frequency, but it is, they try to make it as flat as possible between this 1515 and 1600 megahertz. But that means if we make it longer, it is still doing some amplification here, and especially in the lower frequencies. And the lower frequency they wanted to filter out for that reason. So then we have the filter, the op amp, another filter, and then we have the power splitter. I do have a picture closer by, and it seems to be the MCL WP4G and some other numbers. I did find something also about that, and here it is, the WP4G Plus, and it is made a 4-way splitter without the phase shift for 50 ohms, and it is splitting between 1400 and 6060. And because this split is very narrow, they use this RF magic to split. You also have very low loss, and this is a split in 4, so theoretically it will be around 6. And because they say here already insertion loss dB above 6. Well, 6 is the theoretical. If you go to 4, if you split in 2 you get 3, in 4 you get 6, and there's a little bit on top. So I think they say a maximum 1.4. So that means if you have the LNA, you need at least to do 7.4 dB extra to only for the loss of this device, and then you have the 2 filters as well. So I think if you are somewhere between 2016, then we are correct to end up with a nice amplification with and maybe even a little amplification instead of a loss in total. I'm also looking now a bit at the performance chart, and we can see it is perfectly made for this 1500 megahertz. Of course, when you go too low, it doesn't work. And here also, and we probably see the isolation also between the channels, also here on the top. Do we have that also? Yeah, here we see the isolation. It is the lowest here, exactly in the frequency where we want it for the for the GNSS around this 1575. Well, it's very closely designed to that indeed. And then later, especially in the higher frequencies, of course, the isolation goes down, because then it can just jump over from one to the other channel. So that is the V1 splitter. I have this one, I think, already for 2 years. I'm still very happy with it. It runs 24 hours, 365. So it's really always on. It doesn't get hot. I don't think it takes too much power, because my GPS is not complaining that it's also running 24/7, 365. So it is durable. The V2, I don't know yet. Let's have it too. Okay, there we have the version 2. Well, I put it exactly the same. We have here the input. We have a diode for the turnaround, probably for the polarity. We have a C here. I do have a little coil here, and this seems to be then the U1, the amplifier, the LNA, and then we have some coupling, and the splitter is here done just like I showed with the resistive. It splits first in two here, and then we have another one splits into here, split into here, and the same here. It's split into, it's split into. So here we have again the split for 3 dB, this one split again 3 dB, so we have again between the whole circuit theoretically 6 dB. Here we have 3 plus 3 is also 6, here we also have 3 plus 3 is also 6. So that is the same. Instead of this little black one that immediately split it into 4, we have here just 2 different splits. But I am missing the filtering. So I'm a little bit surprised. So the main thing we need to look at here is the LNA chip that they use now, because why they think they don't need filtering, and they did do that in the V1. So closer look, indeed I don't see any filtering. I see indeed here a little diode, a DC decoupling, then a little coil, and here is the amplifier. And I think it says 1191. So I started searching for GNSS and 1191, and then I found this ad on the internet, and indeed they say, oh, it amplifies from 1164 up to 1610, and that seems exactly the frequency that we also saw on the specifications of the V2. Then I looked a little bit further to the specifications, and you see here, if it is the 1191, then it amplifies all the way from these GPS channels up to a 1610 here, including the GLONASS that is in this little top, because usually it would only be in this area. Let's have a look at this LNA that we use here. Yeah, it's a wideband, low noise, that is good. But we didn't see the filters, so maybe it's not needed with this one, because it is just designed different, that it only amplifies in those frequencies. So let me see if we can find something. So I can see the gain between these frequencies is somewhere between 15 and 19. Well, we already saw that we sort of needed that because of the loss that we need to gain. Yeah, here we see a lot better that the gain is indeed also sort of in the middle, around this 1500 and a bit, and then in the lower frequency it already goes down. It's a pity they don't show all the frequency range, because I was wondering how steep this line is, because we are not using filtering to filter out this lower and way higher frequency. So that's a pity we don't see. Yeah, here I'm looking at these S11, S21, S12, S22. This is like SWR and the impedance of the op-amp itself. And we can see here that it is indeed peaking around the frequency where we want. And if we go much higher, the SWR or the impedance just changes so much that it is probably not effective at all. And here we also see that it start to drop quite a bit in the lower and in the very high frequencies here. So I think that is probably why they didn't use the filters, or probably it was could also be cost related. But when we look at these specs, it is possible. I don't think the quality will went a lot down without the filters, just by using this specific op-amp. I'm here also looking at you have these examples how you can build a circuit, and also here they don't even mention the filters. They just say, oh, you put the RF in, you put a little coil, we've seen that, and then you have the RF out, and that goes in our case directly to these power splitters. So even in the proposed design they don't put it. So I do think that there is enough filtering, or the amplification curve is constructed that it stays within the frequencies that we actually need. So that's it. Splitters for GNSS DO or GPS DO. Thank you for watching, and hope to see you next time.